So now we will see the representation of a heap or how we can implement a heap. So a heap can be implemented as an array. So we can implement the heap as an array by recording its elements. So by recording its elements in top down and left to right fashion. So top to down and left to right fashion. So you can represent or implement the heap as an array by recording its element in top down and left to right fashion. So we will see one simple example on this. So assume we have a heap and the elements are like this, or the nodes or key values are like this: 16, then 14, then 10, then 8, 7, so 9, 3, 2, 4, then 1. So we have discussed this structure as a heap earlier. So also you can verify. So it is a complete binary tree and all the key values of the parent are greater than the children. So 16 is greater than 14 and 10. Similarly 14 greater than 8 and 7. Similarly 8 greater than 2 and 4. Similarly 10 greater than 9 and 3. 7 greater than its child 1. So for all the parent nodes, it is greater than for all the parent nodes, the value is greater than its children, and it is a complete binary. So we can say this is an heap. So how we can represent this as an array? So here you can see, you can mark its index in an array as 1, then top to down and left to right. So this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10. So these numbers that I have written 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8, 9, 10. Here you can see these numbers are top to down and left to right fashion. And these are nothing but the array indexes. So if I create an array like this, so if I create one array, and the indexes are 0, 1, 2, 3, 4, 5, 6, 7, suppose 8, 9, then you can 10. Okay, so now here you can see we have to put the value 16 at index 1, then 14 at index 2, 10 at index 3. Similarly, this 4, 8 as index 4, 7 as index 5. So 8 at 4, 7, then here you can see 9 at index 6, 3 at index 7. So like 9, then 3. For index 8, the value is 2. So it is 2, then 4, then 1. Okay. So in this way, we can represent this heap in an array, and the index values are from 1 to 10. So we are starting from the index 1 and the last node is at index 10. So in this way you can represent. So here you can see there is a relation between the parent and children according to the node index or according to the array index. So here you can see if we want to find the parent node of index I, then simply we can write I by 2 floor or floor of I by 2. So consider one example here. Suppose I want to find the parent of this node. So here parent of 7. So what is the parent of 7? So what is its index? 5. So 5 by 2. So what is 5 by 2? So 5 by 2. 5 by 2 floor. So it is 2.5 floor and it is 2. So here you can see the parent of node 7 is at index 2, that means here 14. So here you can see, so the parent of 7 is at 14. Similarly we can take another one. Suppose I want to find the parent of this one, parent of 2. So what is the index of 2? So the index of 2 is 8. So the suppose 8 by 2 floor. So it is equal to 4 floor. So it is equal to 4. So the the parent of this 2, that is at index 8, is the node that is at index 4. So which one is at index 4? 8. So here you can see the parent of this node 2 is 8. So from this array or from this array index we can calculate the parent of any node. Similarly, if we want to find the left child of a node that is at index I, so left child of a node that is at index I, so is nothing 2 into I. So here you can see, suppose I want to find the left child of this one, this 7, the previously we have taken. So what is the index? So its index is 5. So left child will be 5 into 2. So that is at index 10. So for 7 you can see, so for 7 the left child, or let me write it clearly here, child of the node that is at index 5. So it means the left child of this node 7 is at index 5. So if we put the formula, so it is 2 into 5, that is equal to 10. So it means the left child of this node 7, which is index 5, is the node that is at index 10. So which one is at index 10? So index 10 is 1. So here you can see the left child of this 7 is 1. Or you can see from here, so the if we want to find the index of its left child, so its value is 5. So 2 into 5, the left child index is 10. Similarly here, if we want to find its left child, so its index is 3. So 3 into 2, so 6. Similarly for, if we want to the index of its left child, so its index is 2, left child index is 4. Similarly for here, 4 into 8. And if we want to find the right child of a node that is at index I, so we can write 2 into I plus 1. So similarly here you can see, if we want to find the right child of this one, so what is its index? 3. So what is its right child index? So 3 into 2 plus 1, so it is 7. Similarly here, suppose for this node we want to find the right child, So right child should be at index 5 into 2 plus 1, that means 11. So here no node for 11 exists, so we can say it has no right child. Similarly, for consider this one. So what is the index of 8? So 4. So its right child index will be 4 into 2 plus 1, that is 9. Here you can see. So to use this formula, we have kept nothing at index 0. So in the array, the index 0 is empty. So to make this formula work, otherwise if we put some element here, so we have to change this formula. So there will be a different formula. But most of the authors have used this formula only by keeping this index 0 vacant. So you can store here some node, and accordingly the formula is going to change. And most of the authors have used this formula and make this one as empty. So if we want to find the parent of a node that is at index I, so the formula is I by 2 floor, or floor of I by 2. Similarly, left of I, that means left child of the node that is at index I, is 2 into I. Similarly, right child index of a node that is at index I is 2 into I plus 1. So I hope this formula is clear and the array representation is clear. So simply we have to follow top to bottom and left to right direction. Like or serially you can give 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is very simple. So now we will see some problems based on this concept that we have discussed just now. So is the array with values 23, 17, 14, 6, 13, 10, 1, 5, 7, 12 a max heap? So with the values means these values are represented in an array. So from this array we have to build a heap structure or binary tree representation. Then from the binary tree representation we can easily identify. We can also identify from here, but it will be little bit complex. So for that, convert this array representation to binary tree representation or complete binary tree representation. So if we convert, so 23 will be the root, then left child is 7, right child is 14, then the next number is 6, so its left child is 6, then 13, then 10, then 1, then 5, then 7, then 12. So here you can see it is a complete binary tree because we are constructing the complete binary tree. Then now we have to check whether the value of the parent is value of a parent greater than its children or not. So 23 greater than 17 and 14, so it is okay. Now 17 greater than 6 and 13, so it is also okay, satisfied. 14 greater than 10 and 1, it is also satisfied. Then 6 greater than 5 and 7, so it is not a complete binary tree. Here you can see this one is violated. 6 is less than its child 7, so it is not a max heap. So why not a max heap? Because here it is violated. Okay, so we'll move to the next one. Is an array that is in sorted order a mean heap? So you can take one example. Suppose the example is 5, 10, 13, 15, 17, 20, 23, then 27, 29, 31. So like this. Suppose consider this is one array and the array elements are sorted. So 5, 10, 13, 15, 17, 20, 23, 27, 29, 31. So all the elements are sorted. So now we want to construct a tree. So now we want to construct a binary representation of this array and check whether that becomes a mean heap or not. So for this we can make this one as 5 at the root, then 10, 13, then 15, then 17, then 20, 23, 27, 29, 31. So we can add also some more values here. So with this you can see this is a mean heap. So it is a complete binary tree because we are constructing the complete binary tree from the array. Now we will check whether the value of parent is less than equal to its children for a mean heap. So 5 less than 10 and 13, so it is okay. 10 less than 15 and 17, so satisfied. 15 less than 27 and 29, satisfied. 17 less than 31, satisfied. 13 less than 20 and 23, satisfied. So an array that is in sorted order, a mean heap, so yes. You can take any other example and verify. So an array that is in sorted order forms a mean heap. So you can take some other examples and verify that it is always true. Sorted order means, so it is increasing order. So if it is given in explicitly increasing order or non-decreasing order, then that is a mean heap. If decreasing order, then that is not a mean heap. So that will be a max heap. So here I want to add one property or one relation between sorted array and heaps. You can note. So every sorted arrays are heaps. Every sorted arrays are heaps. So if the sorting is in increasing order, so like this, so it forms a mean heap. If the sorting is in decreasing order, that forms a max heap. So we can say every sorted arrays are heaps, but not the reverse one. That means but not the reverse, that is every heaps are not sorted. So every sorted arrays are heaps, but not the reverse. That means every heaps are not sorted. So why? Because in heap we represent the parent child order, not the order of their siblings. So I can write here because, so in short I have written like this, because heap reflect parent child order, not the order of siblings, not the order of siblings. So I hope this one is clear to everyone. So now we will solve some more problems on the array representation of a heap. So consider this question. So consider a binary max heap implemented using an array. Which of the following array represents a binary max heap? So like this array representation is given. So we have to construct the complete binary tree representation from this array representation, or we have to convert complete binary tree representation from this array representation, then we can easily verify. So here you can see for option A, so 25, so let me write in black color this one, sorry red color, so 25, then 12, then 16, then 13, then 10, then 8, then 14. So here you can see we have to verify the parent child relationship. So 25 is greater than 12 and 16, its children. So for this node 25 it satisfies the heap property. Now come to this one, 12, 13 and 10. So here 12 is not greater than 13. So in the question it asks about max heap. So 12 is not greater than 13. So this property is violated here. So option A is not a max heap. So we can eliminate option A. So now we'll move to option B. So let me delete these things. So 25 is the root, then 14, then 13, then 16, then 10, then 8, then 12, 25, 14, 13, then 16, 10, 8, 12. So now we can check 25, 14, 13. So here it is satisfied. Then 14, 16, 10. So here you can see the property is violated. So 14 is not greater than equal to 16. So here child value is greater. So we can also eliminate option B. So that is not a heap. So now we'll move to another one, that is option C. So 25, 14, 16. So 25, then 14, then 16, then 13, 10, 13, 10, 8, 12. So now we'll check here 25, 14, 16. So here the max heap property satisfied. Then 14 greater than 13, 10. So here also max heap property satisfied. Then 16 greater than 8, 12. So here also max heap property satisfied. So we can say this is a heap. The option C is a heap. So now we'll move to option D. So option D, 25, then 14, then 12, then 13, then 10, then 8, then 16. So here you can see directly I am coming to this node. So 12 is less than 16, its child. So here max heap property is violated. So this one is also not a max heap. So only option C is correct. So I hope all of you understood this one, and this question was asked in GATE 2009. So I will move to another one. Which of the following sequence of array elements forms a heap? And the array elements are given. So we have to draw the complete binary tree structure from these array elements and check whether that is a max heap or not, or a heap or not. So now we will check. So I am writing here 23. First I am writing for option A 23, then 17, 14, then 6, 13, 10. So then 6, 13, 10, then 1, 12, 7, 5, 1, then 12, then 7, then 5. Okay, so now 23, 17, 10, we can again verify 23, 17, 14, then 6, 13, 10, then 1, 12, 7, 5. Okay, so here you can see, so I am coming to directly here. So for this node 6, its child node is 12 and another child is 7. So here the property is violated. So here you can see 23 is greater than 17 and 14, so the property is satisfied. 17 is greater than 6 and 13, so property is satisfied. But here you can see for this subtree, so here 6 is less than its child 12, so this is not a heap. So this is not a heap. Now come to the option B. So we'll check whether option B is correct. So 23, 17, 14. So let me rewrite once again. So 23, 17, 14, then 6, then 13, then 10, then 1, then 5, 7, 12. 5, then 7, then 12. So now we have to check. So 23, 17, 14. So here the property is satisfied. Then 17, 6 and 13. Here also the property is satisfied. Now 14, 10 and 1. Here also the property is satisfied. Then 6, 5, 7. So here it is violated. So 6 is less than its child value 7. So 6 is for this part the property is violated, so this is not a heap. Now we'll move to option C. So we'll move to option C. So 23, 17, 14, then 7, 13, 10, 1, 5, 6, 12. So now you can check 23, 17, 14. So it is satisfied. Then 17, 7, 13. So satisfied. So 14, 10, 1 satisfied. 7, 5, 6 satisfied. 13, 12 satisfied. So we can say option C is a heap. Now we'll move to option D. You can check. So 23, 17, 14. So 23, 17, 14. Then 7, 13, 10. 7, 13, 10. Then 1. Then 12, 5. Then 7. So here you can see the property is violated. So 7 is less than 12. So here the property heap property is violated. So you can say this one is not a heap. So here option C is correct and it forms this representation or this array representation forms a heap. So this question was asked in GATE 2006. So simple questions are asking in GATE. So now we'll see another one. So which one of the following sequence when stored in an array at locations a of 1 to a of 10. So a means the name of the array. A of 1 to a of 10 forms a max heap. So it is clearly written that max heap. If only heap is written, you have to check whether that is a max heap or min heap. So now we can see first draw this one. So here I am drawing for option A 23, 17, then 10, then 6, 13, 12, 6, 13, 14, 6, 13, then 14. So I am not moving here, or let me complete. So here the property is already violated. So let me complete. So this is 1, then 5, 7, then 12. So here you can see the property is violated for max heap. So option A is not correct. Now we will move to option B. So let me erase these things and redraw again. So 23, 17, 14. So 23, 17, 14. Then 7, 13, 10. 7, 13, 10. Then 1, 5, 6, 12. 1, 5, 6, 12. So now we have to check the property 23, 17. So it is 23, 17 and 14. So here satisfied. 17, 7, 13 satisfied. 7, 5, 6 satisfied. 13, 12 satisfied. 14, 10 and 1 satisfied. So here you can see option B is a heap. Now we'll check for option C. Option C will check 23, 17, 14. So 23, 17, 14. Then 6, 13, 10. 6, 13, 10. Then 1, 5, 7, 15. So 1, 5, 7, 15. So here you can see the property is violated. 13, 15. Similarly 6, 7 here also violated. So that's why we can say this one is not a heap or max heap. Now we will check for option D. So for option D, 23, 14, 17, then 1, 10, then 13, 16, 12, 13, 16, 12, then 7, then 5. So here you can see the property is violated. So 1, 7 and 1, 12. So this value, parent value 1 is less than its child, so 12 and 7. And in all other cases the property is satisfied. So here it is violated. So you can say option D is also not a heap. So only option B is correct. And this question was asked in GATE 2023. So recently it was asked. So I hope this one is clear, how we can represent a max heap in an array, or we can say from array representation to heap, or from heap to array. So you can easily represent. If one representation is given, you can easily represent in other. Like here the array representation is given, we are constructing the binary tree representation. If binary tree representation is given, you can also construct the array representation. So it is a very simple one, and based on this several questions are asked in the previous exam. So I hope all of you understood.